Okay, here's another example to see the power of the Green's theorem. So let's say you're given two straight paths. You have one path which goes from 1, 1 to 2, 3. That's your C1 going this way. And then you have another path from 1, 4, 2, 3 to 1, 4. That's your C2. So here's C1. That's C2. And then question is to find this line integral, which is actually a sum of two integrals. You have to integrate from here to there, and then you have to integrate from here to there. And that requires parametrizing these paths, right? You have to use line equation to parametrize C1 from here to there, and then C2 from here to there. And then when you have that, then you divide by dt, multiply by dt. You plug in these parameterization into x and y. You also have to FOIL the x squareds. And you do all the work, and you do a gigantic calculation, and at some point you get the answer. Okay? It's not totally impossible. I think given the time, it'll be probably taking like about less than 10 minutes each. So you're going to take like 20 minutes to get the answer. It's not unreasonable to do it directly. However, we want to be smart, and we will try to solve this in a much easier fashion by applying what? Green's theorem. We're going to use Green's theorem. Now, however, let's see, what is the Green's theorem again? You're saying if you have a domain, if you go around in a counterclockwise fashion of this f dot dr, that's same as double integral over what? The entire domain of what function? The curl, which is partial x, partial y, ln dA. That's the Green's theorem that we want to use. Of course, you want to memorize this. If you forget the Green's theorem, then you have to do all that horrible calculation. All right. But if you see this, you see that you need to pick a domain. What's a nice domain that will kind of include these two paths as part of the boundary? A triangle, right? You would pick this one, right? How's that?
Yeah.
Is that good? Okay. So here's what I want to do. I need this extra path, right? I have to name it. What should I name it? C3. I'm so creative, right? C3. So going this way, C3. Then I know that the boundary of D counterclockwise is really C1 plus C2 plus C3. Then, and also let's calculate what this round x, round y of this curl is. Let's see, round x, round y. X is x squared plus 3y. 5x minus y squared. What's that? When this hits this, y squared differentiates to 0 because you're doing a partial with respect to x. So you get 5. And then when this hits this, x squared differentiated by y is 0. 3y differentiated by y is 3. So what do you get? You get 2. All right, good. So here is the equation that you end up getting. On the left side, this single integration over the boundary is really the sum of three integrals. First over C1, then C2, and C3. So you're really trying to do integral of C1 f dot dr plus integral of C2 f dot dr, integral of C3 f dot dr, equals to integral over this triangle of 2dA. And in here, what are we going after? No, we're going after this. Right? No, sorry. C1 plus C3. So we're going after C1 plus C2, this much. Okay? So here's our plan. I want to calculate this, which seems to be easy enough, right? And then I want to calculate this, which requires parametrization a little bit, but it's not too bad, right? And then you do this minus this, that's equal to this. So that's how we're going to approach it. Sounds like a plan, right? And we have only 5 minutes to accomplish it. Let's try it. Okay, first this one. How do you get the area of this? It's base times height, right? Yeah, what's this length? 1, 2, 2, so this is 1. What's this length? 1, 2, 4, so it's 3. Right? So it's 1/2 base times height, which is 3/2. So the area of this triangle is 3/2. And because this is twice of integral of dA over this, that means it's twice of the area, which is just 3. Okay, that was easy, super easy. So the right side came out to be 3. Okay. On the other hand, we have to figure out how to parameterize this. Do you see that this is like the x coordinate is always 1, it doesn't change, right? But the y coordinate is changing from 4 to 1. How would you parameterize such a thing? Just say C3 RT and which one's not changing again? X is not changing, it's always 1. And for the y it's changing, and t goes from where to where? Yeah, actually 4 to 1. So that's the parameterization. So when you take C3 f dot dr, you have to divide by dt, multiply by dt. So dt goes from where to where? 4 to 1. Right? It goes from 4 to 1. And these two values should be plugged in here and there. Right? Okay. So let's continue. 4 to 1. If I plug in 1 for x and t for y, let's see what does this give you. 1 plus 3t. What about this one? 1 for x and t for y, so it's 5 minus t squared. Dot it with, what should I dot it with? 0, 1, because you're differentiating. Not this thing, you have to use a derivative, which is 0, 1. Okay, so that's not too bad. It's let's flip these. I don't like it when this is higher than this one. So it's 1 to 4, put a minus in front. This times this, 5 minus t squared dt. I don't have any more space. Let me compute here. I can move the minus inside to make this as plus t squared minus 5. So here's what I have. 1 to 4 t squared minus 5 dt, which is 1/3 t cubed minus 5t. 4 and 0. Well, it's 4 and 1. It's not as small as I want it to be, but I mean, it's still much better than doing the other way, okay? Believe me. Okay. So 4 to the cube is 64 over 3. 4 times 5 is negative 20. Minus, when you plug in 1, it's 1/3 minus 5. And let's see, 64 minus 1, that's 63 divided by 3, it's 21. Minus 20 plus 5, so it's going to be 6. So we're almost done. We figured out that this is 6, this is 3, and therefore the answer is? Answer is? All you have to do is move the 6 to the other side and you're done. Very fun.
How'd you get?